For 60 years, we've been searching the stars for advanced civilizations, hoping to hear something. But now, that's changing. Hi, Josh here, and on today's episode of the Infographics Show, we're explaining why scientists are done listening for aliens. They're hunting them. In 2021, a team at Harvard University officially launched the Galileo Project. The mission was to scan the universe for anomalous objects, and their secret weapon is AI. The hunt for alien life began in 1960 with Project Oumuamua, when astronomers trained the 85-foot Green Bank telescope on nearby stars, listening for signals from other civilizations. A year later, Frank Drake created the Drake equation, a cosmic math game estimating how many intelligent civilizations might exist in our galaxy. By 1963, the Arecibo Observatory, a dish 1,000 feet across, was scanning the water hole, a specific frequency band between 1,420 and 1,720 megahertz, hoping to intercept a message from the stars. In theory, it was a good idea, but that's all it ever was. Radio searching relies on intent. The search relies on the idea that alien civilizations are intentionally sending a high-power signal straight at the Earth 24/7 for centuries. If the transmitter sweeps by, then the astronomers have only seconds to catch it. If they're looking at the wrong star at the wrong second, it's gone. It was always a long shot. The Milky Way contains anywhere from 100 to 400 billion stars. Even with the most advanced arrays like the Alien Telescope Array in California, the search covers a tiny portion of the sky. And there's another problem. The sensors are blinded by the Earth's own noise. GPS, military radar, TV broadcasts, the search is drowning in local interference. In 2020, astronomers thought that a signal had been caught from Proxima Centauri. It was a perfect candidate, a narrow-band signal at 982 megahertz. It shifted frequency in a way that suggested it was coming from a moving planet. For a brief moment, scientists believed that there was life. But that excitement didn't last. The signal wasn't from aliens at all. It was just everyday electronics accidentally combining to mimic a cosmic message. Essentially, listening for radio waves is incredibly limited and unlikely to succeed. But there was an answer from an unlikely source. In October 2017, Hawaii's Pan-STARRS telescope spotted a strange object breaking all the rules of orbital mechanics. It was cataloged as 1I 2017 U1. It's known as Oumuamua the Scout, and this was no ordinary rock. Unlike typical asteroids, which are roughly round from billions of years of collisions, Oumuamua had a strange elongated shape, estimated to be between 300 and 3,000 feet long and between 35 to 548 feet wide. It was the light curve that gave it away. As it tumbled through space, its brightness changed by a factor of 10 every 7.3 hours. A normal asteroid shifts by a factor of 3 at most. To reach 10, the object had to be extreme, either a flat pancake or a long, thin cylinder. But the shape wasn't the threat. Oumuamua was traveling at 59,000 miles per hour. It wasn't orbiting the sun, it was slicing through our galaxy. Its path shows that it came from beyond the solar system, making it the first known interstellar visitor. And that was when it did something impossible. It accelerated. Normally, a comet speeds up near the sun because its ice boils off, a process known as outgassing. This creates jets that act as thrusters. But Oumuamua had no tail, no coma, the fuzzy envelope of gas and dust around a comet. The Spitzer Space Telescope looked for carbon-based gas. Nothing. Ground-based telescopes looked for dust. Nothing. If it's not gravity and it's not gas, then what's pushing it? Avi Loeb, the former chair of Harvard's astronomy department, had a theory: solar radiation pressure. If an object is less than 0.04 inches thick and very wide, sunlight pushes it like wind on a sail. But nature doesn't make rocks that thin and 100 yards wide. The scientific community scrambled. Attempts were made to explain it away with theories about hydrogen icebergs or dust bunnies, microscopic particles of ice, rock, and metal that cling together. These objects would be invisible to sensors but could still outgas. But hydrogen icebergs are a theoretical concept. For Loeb, the data was the data. Oumuamua was the first hard evidence that the solar system isn't empty, and there is traffic that is simply passing through. And that is where the Galileo Project came in. The strategy is to build a global network of all-sky observatories. The first is already active at Harvard. Standard telescopes look at a tiny pinprick of the sky for hours, useless for catching hypersonic unidentified anomalous phenomena or UAP. Galileo sensors watch an entire hemisphere 24/7. Optical cameras with fisheye lenses captured the whole sky in high resolution, enough to resolve surface features from a distance. Coupled with passive infrared sensors, They detect heat from propulsion and atmospheric friction. Now the thing is, the system uses passive audio. It listens for the acoustic signature. So does the object create a sonic boom, or is it silent? Does it emit a hum? This is where the custom AI takes over. The team is training machine learning algorithms to filter the entire sky. Millions of images are fed into the system, including things like birds, drones, and planes, Starlink satellites, weather balloons, and the AI learns the flight characteristics of each. It learns that planes bank when they turn. It learns that birds flap. It learns that a satellite moves in a linear, predictable arc. Once the AI learns the background noise, it deletes it, discarding 99.9% of the data. Only anomalies get flagged. The AI doesn't know what a UFO looks like. It doesn't have a picture of a flying saucer in a database. It just looks for physics that shouldn't exist. It looks for the absence of expected features. But the Galileo Project realized that looking up is only half of the battle. If traffic had been passing through the solar system for billions of years, some of it must have crashed. In 2019, Avi Loeb and Amir Siraj gained access to the Center for Near-Earth Object Studies database. This is a catalog of meteors tracked by the U.S. government spy satellites. These satellites are designed to spot nuclear missile launches, so the data on atmospheric entries is extremely accurate. A target was found from January 8, 2014. A meteor roughly 1.5 feet in diameter exploded over the Pacific near Papua New Guinea, but the data was impossible. Known as IM-1, Interstellar Meteor 1, it hit the atmosphere at roughly 28 miles per second, and this reveals clues about its origins. Objects orbiting the Sun have a speed limit, and IM-1 broke it. It wasn't trapped by the Sun's gravity, it came from deep space. But that was just the beginning. When a meteor hits the atmosphere, it faces a wall of air, building pressure until it explodes. Ram pressure. IM-1 didn't explode until the lower atmosphere, withstanding 194 megapascals of pressure. Out of all of the 273 meteors in the CNEOS catalog, IM-1 was considered to be the toughest meteor on record. And this raises a chilling question. Why was the very first interstellar object ever detected also the toughest material ever seen? Loeb suspected it wasn't a rock at all. The suspicion was that it was a fuselage of a probe. The U.S. Space Command later confirmed in a memo that the trajectory data proved its interstellar origin with 99.999% certainty. That was the green light that astronomers were waiting for. In June 2023, the Galileo Project launched a recovery mission. A ship, the Silver Star, was chartered to sail to the impact zone off the coast of Manus Island. The target area was 6 miles long, the depth was 1.2 miles. The mission was to find the remains of an object the size of a microwave that had vaporized 9 years ago. A magnetic sled was built and lowered on a winch and dragged across the ocean floor, hoping to catch magnetic particles. The hunt was on for spherules. When a meteor or a spaceship burns up, molten material rains down as tiny droplets that harden into perfect spheres in the water. For weeks, all they found was black sludge, volcanic sand, dead plankton, and human debris. The crew worked in shifts, scrubbing the magnets and examining the sludge under microscopes. And then they found them. Tiny metallic marbles less than 0.04 inches in diameter, gold, blue, and brown spheres that stood out against the black volcanic ash. Over 700 of these spherules were collected. They were brought back to Harvard and put under a mass spectrometer. And the results were shocking. Analysis revealed a pattern called BELAU, high levels of beryllium, lanthanum, and uranium. The chemical fingerprint points squarely to Earth, specifically coal ash. The uranium isotopes match our planet exactly. In fact, Loeb's team had to rely on iron isotopes, not uranium, to make the case for an extrasolar origin. This would suggest two possibilities. IM-1 came from a region of the galaxy where the chemistry is fundamentally different, or the material is artificial. Beryllium and lanthanum appear in human alloys for heat resistance and durability, used in aerospace landing gear and heat shields, and uranium is used for fuel. If this was a natural rock, it's a rock unlike any ever cataloged in the history of geology. If it was artificial, the melted fragments of an alien probe might have just been recovered. The implications of IM-1 Oumuamua have fundamentally altered the strategy for the next decade. The Galileo Project is planning the next phase, Interception. Chile's Vera C. Rubin Observatory uses a 3,200 megapixel camera to scan the entire southern sky every 4 days. At this level of sensitivity, seeing another Oumuamua once a decade is actually a conservative estimate. These interstellar objects might appear even more often than we realize, anywhere from a few per decade to several per year. AI models even suggest millions could be inside Earth's orbit right now, too small for older telescopes to see. And that gives scientists the chance to do the unthinkable. Project Lyra proposes using a probe to chase an incoming interstellar object, but the physics of interception are brutal. Catching an object moving at 60,000 miles per hour requires an enormous change in velocity. Landing on it isn't required, it just needs to get close enough to capture high-resolution photos. But this brings the mission to the ultimate frontier. Let's say the Galileo Project succeeds and a probe is found, or a signal is intercepted that is complex enough to be a message. How is communication established? Once that breakthrough happens, the realms of science fiction become real. The chances of finding a live alien civilization might be low, but less than a fraction of a percent of the cosmic neighborhood has been scanned. The AI is waking up. The telescopes are opening their eyes. Now go check out What If a Massive Asteroid Was Headed Towards Earth, or click on this video instead.